Hello to you all. We want to go through the power supply completely and in detail. We're going to explain it so you can understand what the structure of a power supply is like and how it works. From the moment electricity enters the power supply to the moment we get output, how does this process happen and what events take place? Here, we see a switching power supply specifically for computers, which has two heat sinks, the first heat sink and the second heat sink. The first heat sink, usually the transistors are actually attached to it, and it dissipates the heat from the primary circuit's transistors. The second heat sink you see here is usually related to the Schottky diodes that are present in this power supply. Alright, so that I can give a better explanation, I had previously prepared a power supply here and removed the heat sink so we could access its components more easily. So we'll start working on the power supply like this, by disassembling it. If I show you the back of the power supply first, here you can see the separation between the primary and secondary circuits. This part is the secondary circuit, meaning this side, and this part is the primary circuit. When you connect power to the power supply, here, through these wires that are placed, which you can also see in this power supply, are in the form of a socket. But since I opened up this power supply, it's easier to see. I'll explain again using this open power supply. Electricity enters from here, passes through a fuse, which you can see here is a glass fuse. Up to this point the electricity is AC, meaning 220 volts AC. It passes through here and then enters the bridge rectifier, which you can see here, the electricity goes into the bridge rectifier. It gets converted to DC or direct current, and then it goes into the capacitors, which you can see here. You might see different types of capacitors in various power supplies. For example, in one power supply, just one capacitor. It might be a 400 volt to 450 volt capacitor, or in some power supplies there might be two 200 to 250 volt capacitors, which together make up 400 volts. As you can see here, there are two capacitors. There are 200 volt capacitors that are connected in series, so together they can store up to 400 volts. So the 220 volt AC power enters the bridge rectifier, and when it's converted to DC power and comes out, its voltage actually increases a bit, and if you use a multimeter to measure the voltage of the capacitors, you'll see that the multimeter will show you a voltage of around 270 or even 300 volts, which I'll demonstrate for you practically right here after the explanations and in the next sessions if we don't get to it in this one. In the next sessions, the DC electricity that actually enters the capacitors after passing through the capacitor section enters the transformers. But there's a problem here. Transformers, or what we call transformers, can never operate on DC electricity. So how does this DC electricity actually enter the transformers? In fact, before this DC electricity enters the transformers, it is converted back to AC by a circuit placed here, which is also called the start circuit, and by the transistors you see here. In other words, we will actually have the same 300 volts AC, but with frequencies that are adjustable, meaning this is the fundamental principle behind the operation of switching power supplies. Based on the circuit that has been designed here, which will be explained more and more, and in the next sessions you will become more familiar with them. There are circuits placed here that, with the help of the transistor, generate various pulses and frequencies. These frequencies or sinusoidal waves that enter the transformer actually pass through the transformer again. And the transformer, by reducing the voltage, generates the output voltages for us. So, the initial circuit works like this. The electricity enters here, passes through the bridge rectifier, goes through the capacitors, and is stored in the capacitors. Then it enters the start circuit. Here, through the transistors and other circuits present, such as the capacitors you can see here, and the resistors that are placed here, the current is once again converted into a sinusoidal wave or sinusoidal pulse so that the transformer can use this wave. Now why is it converted back to AC here? You see, when, for example, the 300 volt electricity passes through one of the transistors, its voltage decreases. For example, it becomes 50 volts. This 50 volts is then converted from a DC wave to an AC sinusoidal wave using a converter circuit. And with an adjustable frequency set by the circuit, it enters the transformer, where the transformer reduces its voltage again. For example, if 300 volts enter the transistor, the NPN transistor placed here drops it to 50 volts, and then it passes through an AC circuit again, a circuit that is actually an oscillator, and converts DC power to AC. Again, that 50 volts comes through. Of course, the 50 volts is not constant. In different power supplies, these voltages may vary. So, the number I mentioned for the transistor is just an example. Here I'm using 50 volts as an example. This 50 volts of electricity passes through the transformer, and for instance the transformer reduces the voltage and it turns it into 12 volts or 5 volts, and in this way it passes through the transformer and the output power comes out. Here, as will be explained further, it comes to this point so that it can be used. So if you see a power supply that is not turning on, for example, it won't power up, the first thing you should do is test the primary circuit. Here, because at first we need to see whether the primary circuit is actually functional and can conduct electricity properly. If we are sure that the primary circuit is healthy, then we should move on to the next circuit. So the path you need to follow starts with the fuse. When a power supply doesn't turn on, you need to check whether the fuse is intact. After the fuse, there's the bridge rectifier, which you should check, and after the bridge rectifier come the capacitors. The ones that are most likely to fail should be checked. Of course, a faulty capacitor doesn't cause the power supply to not turn on. It just might make the power supply struggle during operation. Whenever you notice that a power supply can't deliver the required power and seems to be struggling while it's running, you can check these capacitors, because they're actually the main components that tend to fail here. In these power supplies, there are also diodes and transistors located here, especially the two transistors you see here, because the primary transistor you see here is the transistor related to the standby circuit. This transistor is a FET type, and this transistor you see here is related to the standby circuit, and overall this section is the standby circuit of this power supply. The next transistors are related to the output voltages, which generate the required voltages here and perform voltage reduction. In fact, the transformers here are step-down types, so up to this point you've learned that. In fact, there are fuses, pull diodes, capacitors and regulating transistors, and the electricity passes through the transistors. After it passes through a DC to AC converter circuit, it enters the transformers, and the transformers either amplify or reduce the voltage and produce the output. Now the electricity at the output section is AC, but with a voltage, for example, of 12 volts. In fact, the transformer only generates the positive voltage, the positive electricity. Here we have it at the output. Now to make this electricity usable, they use Schottky diodes for the output electricity, which you can see here. In this image you can see it completely, and as you can see you can even recognize it by its symbol. You can identify that the type of diodes are Schottky diodes. For example, the Schottky diode used here is a common cathode type. So the positive electricity passes through the Schottky diode and is once again converted into DC electricity. And its current is limited by resistors and capacitors. The desired voltage is generated and it is delivered at the output. And that's basically how a power supply works. Now, aside from the input path, the converter, and the output, we also have a circuit called the standby circuit. The standby circuit, if your power supply is plugged in, the standby circuit is always on. This standby circuit, which actually includes this section, as you can see, this part has more components, it's packed with them. That is starting from this first transistor, the first transformer and the components around them. These make up the standby circuit. This standby circuit is connected to a control circuit, and the control circuit, it's also the circuit that actually allows you to turn the power supply on and off remotely. The control circuit is usually connected to a wire. In fact, it's connected to a green wire, and that's why we pulled out the green wire from this power supply for repairs. But its place is still there, and I can show you. Here you can see a small green wire. This green wire, along with the other wires, comes out toward the output, and the electricity in the green wire is related to the control circuit. It's 5 volts positive. That means if you take the power supply and want to measure the voltage of the green wire, you'll see that it's 5 volts positive, which will also measure and show you on other power supplies. The standby circuit also has its own wire, which, in fact, if you find a purple wire among the output wires of the power supply, that's the voltage for the standby section, which you can also see here. Take a look. The purple wire you see here is related to the standby circuit. After the standby circuit and the control circuit, there's another circuit called the overvoltage circuit, which actually monitors the output voltages. That means every voltage you see here that has an output. Each of these voltages sends a feedback signal to the overvoltage circuit, which is related to this section. Now, what does the overvoltage circuit do? The overvoltage circuit monitors the output voltages of this power supply. For example, making sure that the 3.3 volt voltage isn't higher or lower than it should be. The same goes for the positive 12 volt, the positive 5 volt, and all the voltages, their outputs should actually be normal. If any of these voltages have an output that's above or below a certain limit, the control circuit, which is managed by the IC and is actually located in this section, detects any abnormal or improper output current. and ultimately instructs the control circuit to shut down the power supply. The control circuit then completely shuts off the power supply, but this only happens if the power supply itself is actually healthy and functioning properly. Switching power supplies, since they are made up of different sections, can have each section fail independently. For example, if the control circuit of a switching power supply becomes faulty, when the voltage in the circuit exceeds the limit, it is supposed to signal the control circuit to shut down the power supply. But this doesn't happen, and the power supply stays on and keeps running right up to the point of failure. So, by troubleshooting step by step, we can determine whether the control circuit is working properly or not, whether the overvoltage protection circuit is functioning, and whether the standby circuit is operating correctly. These are all things you need to diagnose in a power supply, and in this training series you will learn all of them thoroughly. So if you come across a faulty power supply that, for example, doesn't turn on, you need to investigate a specific section. If you see a power supply where the standby circuit isn't working at all, how should you troubleshoot the standby circuit? There's a method for that, and you need to test a particular section. Not all sections are related. For example, a standby circuit failure has nothing to do with the output circuit or the primary circuit, so we should only test the standby circuit. If the control circuit is faulty, we need to test the control circuit, and if the overvoltage circuit is faulty, we need to test the overvoltage circuit. And if our output voltages are not correct, and we see, for example, that the 12-volt line is giving 11 volts, or maybe it's giving 13 volts instead. In this case, you need to check the components related to the output, such as Schottky diodes, MOSFETs, inductors, and so on. Test the regular diodes placed here and even the capacitors. Their job is actually to stabilize the output voltage. So anytime you see a power supply like this, it can have its own specific faults. You need to keep these issues in mind when troubleshooting. Alright, so here we've covered things in a fairly detailed and thorough way. The different sections of the power circuit were explained, so you can start troubleshooting using a multimeter. But the first thing we want to do is, the first step is to measure the output voltages of a power supply. Here we've prepared two power supplies, one that's faulty and problematic, and one that's working properly. Using a multimeter and a power tester, we're going to show you how to identify a faulty power supply and distinguish it from a working one so that we can move on to troubleshooting it. Alright, here we've prepared a power supply and we're going to test it. You see, when you turn on the power supply, here by plugging it in and switching it on, the fan starts spinning. This means the power supply is on. Of course, to be able to turn on the power supply, you can connect the green wire and the black wire that are located in this connector. You can connect them using a piece of wire or a pair of tweezers. If you want to test a power supply more thoroughly, you can completely separate the green and black wires like this, cut them, and then connect them together here. Which is what I did here, and I usually do this for test power supplies. But for power supplies that you want to repair and give back to a customer, you should never do this under any circumstances, and only connect the wires together at the connector here. The green and black wires, the green wire is for turning on the power supply and carries plus 5 volts, while the black wire is 0 volts. Now, regarding the power supply wires, remember that the black wire is always negative. It doesn't matter, the black wire is always negative, no matter which connector the black wire is in. Look, in this connector or any other connector you plug in, the black wire is negative and the yellow wire is positive 12 volts. So, if we want to measure the voltage from these wires, it should show us positive 12 volts. The red wire is positive 5 volts, and when we test it, we can see whether it gives 5 volts or not. The orange wire is also positive, meaning it should show us 3.3 volts. And the blue wire you see here, in some power supplies it's a lighter blue, in others it's a darker blue, but it doesn't matter whether it's light or dark blue. The blue wire is also negative 12 volts. The gray wire you see here is related to the power good wire, which is actually the same as the signal wire. It indicates the power status and sends the power health status to the motherboard. It notifies that if the power health status is not good, the motherboard, especially newer motherboards, will issue a shutdown command to the computer so that the components are not damaged. And also, if you find a white wire in a power supply, that white wire is negative 5 volts. Now we want to test it. Let's see if the output of this power supply is correct and if it actually gives us the real voltages or not. Here we prepare the multimeter since the power supply output is DC voltage. So we set the multimeter to DC test mode and place it here. We connect the negative probe or the black wire of the multimeter to one of the black wires. Here I bring one of these sockets and connect the black probe to the black wire. so it remains securely in place like this. And then I use the positive probe to measure the voltages one by one. For example, I start with the orange wire. When I connect the probe to the orange wire, as you can see right here on the screen, the voltage that it is currently showing me here at this moment is displayed. First of all, it's fluctuating, and the voltage it's showing is 6, 2, and 5 volts, which is completely inappropriate. Okay, now let's carefully test the red wire. Here I am connecting the probe to the red wire, making sure the connection is secure. You can see that the multimeter is showing a voltage of 6 to 7 volts, which is also fluctuating and is not a suitable voltage at all. Okay, now I'm going to test the 12 volt wire, which is the yellow wire. I bring the yellow wire here. I can even use the next pin, which actually makes the test easier for me, as you can see. Here I connect the positive lead to the yellow wire, and you can see the result here. Well, the 12 volt positive is also fluctuating, meaning that in terms of output voltage, this power supply doesn't have a suitable voltage at all. Now, to be sure about our test, we're going to test the power supply using a power tester. We're going to connect this power supply to the power tester. Like this. You've already become familiar with the power tester in the previous session, right? Take a look at it like this. I'm connecting the socket. And to provide the proper voltage, I'm also connecting its 4-pin connector. As you can see here, the power tester is showing us a fault in this power supply. Take a look. The negative 12 volts is fine, meaning it's acceptable, and the positive 12 volts is also acceptable, but the 5 volt standby is problematic. In this power supply, the voltage is higher than what it should be. It should be 5 volts, meaning the standby voltage. It should be 5 volts, but here it's showing me 2 H's. That means high voltage, meaning the standby voltage is higher than normal, and it's not standard. The power good, which is indicated by the PG symbol, here it's showing 350, and it's not blinking for now, which means the power good of this power supply is also fine. The 3.3 volt output is also appropriate, as well as the plus 12 volt and plus 5 volt outputs. Alright, now I want to teach you the ABA method. At first it showed us like this. Now let's power it off once. I'm turning it off and turning it back on again. That is, I'm unplugging it and plugging it back in. Well, as you can see, once again it's showing us that the standby voltage is not suitable and the voltage is not appropriate for the device. This indicates that the voltage provided is still not meeting the necessary requirements. And after a while you can see that even the 12 volt voltage turns into LL, meaning the voltage is low. So the information and feedback that the power tester gives us indicates that the power supply here actually has improper voltages and needs repair, and it's not outputting proper voltages at all. When you connect this power supply to a computer and try to turn the computer on, first of all, it will damage the motherboard. Secondly, you'll notice that the computer either restarts by itself, or when you open a heavy program, it shuts down or restarts on its own, or it might not turn on at all, just giving an initial start but failing to fully power up and boot. It keeps shutting down, restarting, and generally acting up and causing interruptions like this. If you see a computer that keeps restarting on its own and can't operate continuously, first, before you check the motherboard, other devices or other parts of the computer, test the power supply. So here you saw what a faulty power supply looks like. Now instead of the faulty power supply, I want to bring in a working one so you can see what a healthy power supply should be like for yourself. Based on the video you just watched, see how different a healthy power supply can be from a faulty one. Here, as you saw, the output voltage of this power supply was not suitable. Now, I'm going to replace this power supply with a working one. So here, we're looking at a healthy power supply. I'm going to use a power tester to test this power supply as well. Here's how I do it. Basically, I connect its sockets like this, just like this. I also connect its 12 volt socket, which is a 4-pin, and now I'm going to turn on the power supply. After connecting the sockets to the power tester, I press the power button here to turn on the power supply. You can see that the power supply fan started spinning, so here you can see that everything is okay. Negative 12 volts, positive 12 volts, 5 volts. The standby light on this power supply isn't blinking, which means it's healthy. The power supply is good. The voltages are in the proper range, positive 5 volts, positive 12 volts, and 3.3 volts. And you can see that the power tester isn't showing any errors at all, not even a beep. And a healthy power supply should behave exactly like this. That is, when you test it with a power tester or a multimeter, the output voltage should be completely stable and shouldn't fluctuate. After testing with the power tester, now we'll move on to testing with the multimeter. I'm going to turn off this power supply again. We'll test the same power supply using a multimeter as well to see what its output voltage is like. Since I've disconnected the power tester, I need to come here. We can see the green and black wires here, and using a pair of tweezers, I need to connect them together so the power supply turns on and I can test it. Here I'm bringing a pair of tweezers. Try to use the tweezers you see here, which are black handled and commonly known as Z tweezers. So when I connect the green and black wires together, you can see here that the power supply starts working and the fan begins to spin. At this point, I use a multimeter to measure the voltages of the power supply. I've connected the negative probe to the negative wire, and now I'm going to measure the voltage here. First I'll check the 12 volt line. If you can see the multimeter, you'll notice that the 12 volts here is completely stable. The fluctuation you see is due to the hand tremor. This power supply is actually very stable. It's working properly and giving us the output voltage. Now let's move on to the 5 volt line and test that as well. In this image you can also see that the 5 volts from the power supply is stable, although there might be a very slight margin of error. If this error is a measurement error, it doesn't cause any problems for the computer. As you can see, the 5 volts here is also stable. Alright, now let's test the 3.3 volts. Here as well, you can see the 3.3 volts, and in fact the voltage is appropriate and the output voltage of this power supply is completely stabilized. As mentioned before, the small error you see here could be due to the multimeter, and even if there is an error, this error is permissible. All components and devices have an allowable margin of error, and this does not cause any problems. So as you saw, the output voltage of this power supply is actually completely appropriate, and this power supply is in perfect working condition. You can easily compare it with other power supplies yourself, especially the one we tested at the beginning, before this one, where you saw how unsuitable its output was. There is a very important point here that you need to know whenever you want to test any power supply. First and foremost, always connect it to a test lamp before plugging the power supply directly into the electricity, especially with power supplies whose condition you are not aware of, because if you connect the power supply to electricity and it has an internal short circuit, as soon as you plug in the power supply, the circuit breaker will trip, and this sudden short circuit can even cause damage to other devices like your TV, refrigerator, and so on. Therefore, the test lamp allows you to connect a power supply to electricity without any risk. And if you see that connecting a power supply to the test lamp causes the lamp to light up, that power supply has an internal short circuit, and if you plug it directly into the electricity, the circuit breaker will trip. But if you see that the lamp does not light up, it means the power supply does not have a short circuit and you can work on it more easily. Now, in addition to the fact that if you plug a power supply with a short circuit directly into the electricity, it can cause other components in that power supply that were still good to burn out, and the power supply might even catch fire. But if you connect it to the test lamp first, this won't happen. So, whatever work you do in the electronics workshop, make sure to get its power through the test lamp. And that's why the test lamp is one of the most important tools. And if you want to know how to make a test lamp yourself, I suggest you check out the link below. So you know how to make a test lamp for yourself and use it. To actually understand how the test lamp works, I've brought a power supply here, which is also faulty, and its problem is that it has an internal short circuit. If I turn on this power supply, it will cause the test lamp to light up. Since it's not possible to change the camera angle towards the test lamp, only the light from the test lamp will fall in this direction, and you'll be able to see it. Watch what happens when I press the power switch. To make it clearer in the video, I'll turn off the main light here. So I'm actually turning off the light here. Alright, now when I press the power switch, you'll see a yellow light appear. This yellow light here is from the test lamp. That means if I plug this power supply directly into the electricity, it will trip the circuit breaker and might even damage the power supply itself. Here it could cause a short circuit and burn out, which is why it's always recommended to use a test lamp. Let me show you again. I'm turning the power supply on. You can see that the test lamp's light is clearly visible here. This means the power supply has a complete short circuit. That's exactly why you're told to always use a test lamp. This power supply actually has a damaged primary circuit, and if I bring the power supply a bit closer, you can even see the burn marks Let me unplug the power supply to avoid any danger. I'm bringing the power supply a bit closer to the camera, and at the bottom of the power supply inside you can see that this part is completely blackened, and the components, even the board, the components are completely burnt. That means the primary circuit of this power supply, especially the transistors here and on the first heatsink, are completely burnt as well. Be sure to use a test lamp in the workshop here so you don't run into problems. So the power supplies that we decided to repair in this session, one is this power supply which is burnt and has a complete short circuit, and the other is a power supply that was shown to you at the beginning and actually had an output voltage problem. We've selected these two power supplies for repair in this training series so that you can get familiar with the troubleshooting method for power supplies, since here you've already learned about some of the faults. We've fully explained it to you in this session, and now we want to move on to its repair. Even with this burnt power supply, if we want to take another look at it, you'll see that there are even problems in the capacitors and the output voltage, and some components are faulty. Take a look. Here, for example, one of the capacitors and the second one, two of the capacitors on the output voltage side are swollen, and their damage is completely obvious. What we need to do first is to test the primary circuit. What we want to do is to completely remove the transistors that are here. These are FET type transistors, and let's test its circuit, check the connections of the other components, and be able to repair the power supply. Of course, the repair work. We'll start with a power supply that had an output voltage problem so that we can gradually move towards repairs and it won't be too difficult for you. Alright, from the next session, we'll start in more detail, meaning after we've done the setup. Here, you learned what each part of the power supply does and how it works. In the next session, we'll start disassembling the power supply piece by piece and actually carry out the repairs in a fully practical way. We'll continue in this manner so that you can easily do the work yourself. The only important point to keep in mind is that you should definitely do all the tasks we perform here at home as well. Try to get a faulty power supply, even if it's difficult, like the power supply we have here. Even if it's a tough one, try to get it and start working on it. Practice on it so you can properly improve your skills and increase your proficiency in working with power supplies through practice. Simply watching and learning from this tutorial will never give you hands-on experience. What makes you truly skilled is practicing the work yourself. So put this lesson into action and start working on repairing a power supply. Until the next session, goodbye.